Hey y'all, thanks for checking out my course, Python Pandas for your grandpa. So easy, your grandpa could learn it. You probably already know Pandas is Python's go-to package for data cleaning and wrangling tasks, typically for data science and machine learning. In this course, we'll cover pretty much every important aspect of Pandas, like reading and writing data to a file, creating data, merging data, grouping data, and so on. And I've got lots of examples, animations, and practice problems to help you learn intuitively and efficiently. So if you're thinking about taking this course, you should have a basic understanding of Python. Things like data types, lists, sets, and lambda functions. And since Pandas is built largely on top of NumPy, you should have familiarity with the NumPy package. Now, you don't need to know NumPy to take this course, but I'd certainly recommend it. And if you don't really know NumPy, I happen to have a course on that too, called Python NumPy for your grandma, which I'll link to in the description. Lastly, I should mention this course was developed using Pandas version 1.2.0. If you're on a later version, I wouldn't be too concerned, as 99% of what I teach in this course is unlikely to change in future versions. And of course, if you have any questions, feel free to reach out to me and I'll be happy to respond. Alright, so hopefully I'll see you in the next lecture. For this course, I'll be using Pandas version 1.2.0, and I'll be running all my code on Google Colab. Now, if you don't know, Google Colab is a super easy and free way to run Python directly in your browser. It works like a Jupyter aka Python notebook, but you don't have to worry about installing Python, setting up a virtual environment, connecting to an IDE, and all the hassle that comes with those things. You literally just sign up and start writing code. Now, you don't need to use Google Colab for this course, but if you want to, I have a free video on how to set up and get started with Google Colab, which I'll link to in the description. Also, if you have any questions throughout the course, please don't hesitate to ask. Pandas is a vast library of data wrangling tools, but all of those tools are centered around two fundamental data structures, series and DataFrame. If you imagine a table of data, you can think of each column as a series and the structured collection of every column as a data frame. Now, if you know NumPy, you might be wondering, what's the difference between a series and a NumPy 1D array? After all, they both represent a one-dimensional set of values. And in fact, Pandas series actually stores data using a NumPy array. The difference lies in the additional functionality that series has. You can think of a series as a souped-up version of a NumPy 1D array. You'll see what I mean as we go through the course, but to get started, we need to learn how to make a series from scratch. So that'll be the focus of this video. Before we do anything, we need to install and import Pandas. The easiest way to install it is with pip, so pip install pandas. If you're using Google Colab like me, you would use !pip install pandas. Except it's already installed by default, so you don't even need to do that. Once it's installed, we need to import it. The common convention is to import pandas as PD. The easiest way to make a series is from a list, just like making a NumPy array. For example, here we say x equals pd.series, open parens, and then pass in a list of numbers. If we print the series, we get back something like this. Notice how it already looks a bit different than a NumPy array. See that first column of values? That's called the series index, and you can use it to access the series elements in creative and meaningful ways. More on that a bit later. Also notice the output includes dtype int64, which tells us the data type of the elements in the series. Just like a NumPy array, each element in a series must be of the same size and type. You can have a series of ints, a series of floats, and a series of strings, but you can't have a series of ints, floats, and strings together. You can use Python's type function to check that x is indeed a series object. But if you want to check the internal data type of the series elements without printing the whole series, you can use the .dtype attribute, like x.dtype. And here you can see we're storing 64-bit integers. If you wanted to access the underlying NumPy array, you can use the .toNumPy method. You might also see people using the .values attribute here, but this technique is deprecated and not recommended. You can also use the highly popular head and tail methods to pick out the first and last 5 elements of the series. For example, x.head returns the first 5 elements, while x.tail returns the last 5 elements. And if you wanted to pick out the first 3 elements, you would just do x.head open parens 3. Another way you can make a series is from a Python dictionary like this. In this case, Pandas uses the dictionary keys for the series index and the dictionary values for the series values. Again, we'll cover the index and its purpose shortly. For now, just know it's a thing. Also notice, in the first example, we created a series of integers, but in this example, we appended each value with a decimal, so we got back a series of floats. If we wanted to make a series of strings, we could do that too with something like z equals pd.series, open parens, and then pass in a list of strings. If we print z, notice the d type is listed as object. I'll explain why that's so cryptic in a future video, but in the meantime, I want to show you the newer and probably better way to create a series of strings. If we modify this statement by explicitly setting dtype equals string, now when we print z, it lists the dtype as string. Again, I'm sweeping a lot under the rug here, but we'll cover these things in a future video. Now, you might be wondering how I knew the series function included a parameter for dtype. Let's hop over to Google and just do a search for pandas series. If we click on the first link, we can see the full function signature for the series function, which includes parameters for data, index, dtype, and some other things. So this is usually the first place to look when you want to learn or have questions about a function. So far, we've seen how you can make a series from a list and a dictionary, but perhaps the most powerful way to make a series from scratch is to make it from a NumPy array. Before we do that, we need to import NumPy. So we'll import NumPy as np, and then import pandas as pd. So now if we create a NumPy array like x equals np.array open parens list 10, 20, 30, 40, we can convert it to a series just by wrapping x in pd.series. So why is this so powerful? Well, suppose you wanted to make a complex series from scratch, like an unusual sequence of floats or a random sample of values from a normal distribution. The somewhat lame but practical way to do this is to use NumPy. NumPy has lots of great tools for making arrays from scratch, and we've already seen how you can wrap them into a series. So, for example, we could make a series with 10 evenly spaced values between 1 and 2 using the np.linspace function, passing in start, stop, and num parameters, and then just wrapping the resulting NumPy array with pd.series. Similarly, we could make a series of standard normal random values using NumPy's np.random.normal function and wrapping that result with pd.series. So if you can't see where this is going, one of the keys to mastering pandas is actually to master NumPy, since most of pandas is built on top of it. And if you don't feel good about your NumPy skills, lucky for you, I happen to have a course on that too, called Python NumPy for your grandma. I'll drop a link to it in the description. In this video, we'll see how to use the index of a series to access and modify its elements in meaningful ways. Suppose we have the following series x. If you wanted to access the ith element of the series, you might be inclined to use square bracket indexing notation, just like accessing elements from a Python list or NumPy array. And this would work. X square bracket 0 returns the first element, X square brackets 1 returns the second element, and so on. But looks can be deceiving, and what's happening here probably isn't what you think. X square brackets 0 actually returns the element or elements of the series with index label 0. In this case, that element happens to be the first element in the series, but if we mix up the index, which we can do by setting x.index equals a list of integers like this, now x square bracket 0 returns something totally different. So if you want to access the ith value of a series, you should use the series.iloc property. For example, x.iloc square bracket 0 returns the first element by position, and x.iloc square brackets 1 returns the second element by position. Throughout the course, I'll explicitly refer to these as index labels and these as index positions. With iloc, you can also use negative indexing. So x.iloc square brackets -1 returns the last element, and x.iloc square brackets -3 returns the third to last element. Another trick you can do is use slicing to return a subseries. For example, x.iloc square brackets 1:4:2 returns this 2-row subseries. In pseudocode, you could describe this as picking out the rows from position 1 inclusive up to position 4 exclusive, stepping by 2. Notice here we get back a series object, whereas in the previous examples we got back scalars. And lastly, you could pass in a list, array, or series of integers to pick out specific rows of x. Let's take a step back and talk about the index. Every series has an index, and its purpose is to provide a label for each element in the series. As we've seen, when you make a series from scratch, it automatically gets an index of sequential values starting from 0. For example, here we make a series to represent the test grades of 5 students, and you can see how the index 0, 1, 2, 3, 4, 5 automatically gets created. We can change the index pretty easily just by setting it equal to another array, list, or series of values with the proper length. The index values don't even need to be integers, and in fact they're often represented as strings since strings are more descriptive. For example, here we might say grades.index equals the list of strings Homer, Maggie, Grandpa, Bart, Lisa, Marge. Now, if we wanted to know what grade Bart got, we could do grades square brackets open quotes Bart, and we'd get back 89. Now, remember earlier when I said x square bracket 0 returns the value with index label 0, not the value at position 0? That's not entirely true. If you test it out on our grade series, grades square bracket 0 actually does give us the value at position 0. So what gives? The reason this works is because, in this case, our index consists of strings, but we requested the element with index 0, an integer. Pandas basically tries to be smart and figures, hey, this guy passed in an integer, but the index consists of strings. Therefore, he must be requesting the element at position 0. In the earlier example, our index data type was int, so when we requested x square bracket 0, Pandas assumed we were searching for the value with label 0. While this behavior can be convenient and some people like it, I think it's a little bit confusing and obfuscates what's actually going on. So I highly recommend avoiding this square bracket notation. I think it leads to more problems than benefits. Instead, be explicit and use .iloc for positional indexing and .loc for label indexing. For example, if we want to pick out Bart's grade, we could do grades square brackets open quotes Bart, but it's better if we explicitly do grades.loc square brackets open quotes Bart. And if we want to get the second value in the series, we could do grades square brackets 1, but it's better if we explicitly do grades.iloc square brackets 1. And just like with positional indexing, we can use slicing to access a range of elements by labeled index, which is really cool, by the way. For example, we can say grades.loc square brackets Homer, Grandpa to get back every person's grade between Homer and Grandpa, including both endpoints. Note that this type of slicing is slightly different from positional slicing, which excludes the right boundary. For example, if we do grades.iloc square brackets 0:2, we get back 2 rows, not 3. And just like with iloc, we can pass in a list, array, or series of labels into loc to retrieve multiple rows. Before we move on, we need to address a few more things about the index. You may have noticed that when you make a series from scratch, Pandas automatically gives you something called a range index. For example, if we make a series of 10 million random normal values like this, and then we print x's index, you can see it's a range index with start 0, stop 10 million, and step 1. If we make a second series y, but this time we specify the index as an integer array from 0 to 10 million, if we print y's index, you can see it's something called an N64 index. From a high-level user's perspective, you can pretty much ignore this subtle difference. On the surface, these series behave the same way, but internally, these things are significantly different. Perhaps the most obvious difference is that the int64 index consumes more memory than the range index, since it literally stores all 10 million index values, whereas the range index basically stores 3 values: start, stop, and step. You can see this pretty clearly using the sys.getSizeOf function, noting that y is about twice the size of x. Less obvious is the fact that range index actually provides a performance boost over int64 index. When you ask for element 342, range index knows exactly where to go to fetch that data, just by using start and step size. But for int64 index, it's not that simple, since there's no guarantee that the index values jump by a fixed size, or that they're in order, or that there's no duplicates. We'll cover this more later when we start joining data frames together. Now, one advantage int64 index has over range index is that it allows for duplicate index values. For example, you can make a series alpha like this, which has some repeated index values. And then when you do things like ask for the element with label 0, you'll get back every element with label 0. Now that we know how to access data from a series using an index, overwriting data is pretty straightforward. For example, if you have the series foo with values 10, 20, 30, 40, 50, with index labels A, B, C, D, E, and you want to change the second element to 200, you can do foo.iloc square brackets 1 equals 200. If you want to set the first, second, and third elements to 99, you can do foo.iloc square brackets and then pass in a list of indices like 0, 1, 2 and set that equal to 99. Or you could use slicing like foo.iloc square brackets :3 equals 999. This is like saying select every element from the start of the series up to but excluding position 3, and then update those values to be 999. And you can do the same exact operations using the index labels with foo.loc. What if you wanted to overwrite the entire series with a new set of values like the ones in this array? Your first instinct might be to overwrite the entire foo variable like this, but then you'd lose foo's index. Instead, use slicing to select and overwrite all of foo's values without overwriting its index. Now, suppose you have these two series, x and y, each with 4 values whose indices are different but share a few common values, namely 0, 2, and 3. What do you think will happen if we say x.loc square brackets list 0, 1, and we set that equal to y? This one's a bit strange to get used to, but when you see the result, it's pretty clear what's happening. Pandas starts by searching x for the values with index labels 0 and 1. Then it looks for matching labels in y to use to overwrite x. Since x's label 1 doesn't match any elements in y, Pandas assigns it the value nan. And since nan only exists as a floating point value in NumPy, Pandas casts the entire series from ints to floats. We'll talk more about nan in a future video, but basically it's a special value to represent missing or invalid data. Also, note that we could do the same exact thing using slicing. For example, if we do x.iloc square brackets :2 equals y, Pandas selects the first 2 values from x and then searches y for replacement values with matching index labels. If we try to do this using a NumPy array on the right-hand side, we'll get an error, because when the right-hand side is a NumPy array, Pandas tries to assign each element of the right-hand side to the left-hand side on an element-by-element basis. And in this case, we're trying to replace 2 values with 4 values. If the NumPy array on the right-hand side is the same length as the series subset on the left-hand side, this would work, but note that the array elements get assigned to the series subset by position, not index label. In this video, we'll see how you can add 2 series together. And even though we're only talking about addition, everything we discuss applies to other basic math operations like subtraction, multiplication, and division. Suppose you have the following series of integers, 1, 2, 3, 4, and you add a scalar to it. Just like in NumPy, Pandas uses broadcasting to add the scalar to each element of the series. But watch what happens when we wrap that scalar into a series before adding it. When you add two series x and y, Pandas only combines elements with the same index label. This process is called index alignment. Looking back at our example, the temporary series we created, pd.series1, automatically gets an index label of 0, so it only gets added to elements of x, which also have an index label of 0. This behavior causes a lot of confusion because when you create a series from scratch, Pandas automatically gives the series a sequential index starting from 0. So if you make two corresponding series, A and B, and you add them together, it looks like the addition is happening element-wise by position. But that's actually not what's happening. It's easy to see if you reverse A's index before adding it to B. The same behavior holds true for subtraction, multiplication, division, and other basic math operations. So what if you didn't want this behavior? I mean, what if you just want to add A and B element-wise by position? The answer is a recurring theme in this course. Drop down to the NumPy level and do it there. For example, if we do a.toNumPy plus b.toNumPy, we'll simply be adding two NumPy arrays. An addition between NumPy arrays happens element-wise by position. Of course, the result will also be a NumPy array, so you'll have to convert it back to a series if that's what you want. Alternatively, if you add a series to a NumPy array, the addition happens element-wise by position, and the result will be a series with the same index labels as the original series. So if we do a plus b.toNumPy, it works just like the last example, except A's index values are retained in the result. Alright, so what if we have a series x like before, and another series y like this? And we want to add y to x based on matching index labels, but we don't want the result to include NaN values, where x doesn't have a matching index in y. In this case, we can say x.loc square brackets y.index to pick out elements of x we want to operate on, and then plus equals y to add y to those values. In this video, we'll see how to use boolean indexing to select values from a series based on logical conditions. Just like with NumPy arrays, you can subset a Pandas series using a boolean index. For example, if you have a series of integers like this one called foo, if you check foo less than 20, you'll get back a corresponding series of boolean values. If you assign that series to a variable called mask, you can use it to subset foo, picking out values less than 20. Or if you wanted to avoid the intermediate step, you could do a one-liner like this. Now, you might think that the ith value in foo gets returned if the ith value in mask is true. And you'd kind of be right, but watch what happens if we swap the index labels 4 and 5 in foo, and then we do the same exact boolean subset using mask. This time, the result includes 31 instead of 17. That's because foo.loc square brackets mask picks out the elements of foo whose index label matches those of mask where mask has a true value. Usually this is fine, but in some cases it might not be what you want, and if you'd rather just include or exclude values of foo by corresponding positions of true and false values in mask, just use mask's underlying NumPy array to subset foo, like foo.loc square brackets mask.toNumPy. In this case, the third and fifth values of mask are true, so we get back the third and fifth values of foo. If you want to combine Boolean series together, you can do that too using an ampersand for and a pipe for or. Note that when you combine two Boolean series, Pandas matches and combines Boolean values based on their index. For example, suppose we have a series called ages with the age of 5 people and a corresponding series called genders with their gender. Even though their indexes are in a different order, we can still answer questions like who's a male younger than 18? In this case, we make a series to identify whether each person is a male, and a second series to identify whether each person is younger than 18. Then we combine them with an ampersand, i.e. the element-wise AND operator, to identify whether each person is a male and younger than 18. Then, if we assign that to a variable called mask, we can index it with itself to get the names of males less than 18. In this case, the names will be in the index. We can also use the tilde operator to negate a Boolean series. So, for example, if we do tilde mask, we can determine who's not a male and less than 18. In other words, who is a female or is at least 18. And when you combine Boolean series, make sure you wrap each condition in parentheses. Otherwise, the interpreter will read things in the wrong order and you'll probably get an error. For example, if we try to determine people between 18 and 42 like this, we'll get an error. The solution here is just to wrap the conditions in parentheses like this. In this video, we'll see how to use nan to represent missing or invalid values in a series. Let's start by talking about nan prior to version 1.0.0. So back in the day, if you wanted to represent missing or invalid data, you had to use NumPy's special floating point constant, np.nan. So if you had a pandas series of integers like this, and then you set the second element to np.nan, the series would get cast to floats because nan only exists in NumPy as a floating point constant. By the time you're watching this video, this may have changed, but at the moment, fixing this problem is still on the NumPy roadmap. So in the past, you couldn't have a pandas series of integers with nan values because you couldn't and still can't have a NumPy array of integers with nan values. If you wanted nan values, your series had to be a series of floats. Then pandas released version 0.24, which included a nullable integer data type. It's called int64 with a capital I to differentiate it from NumPy's int64 with a lowercase I. So let's rebuild that series ru, this time specifying dtype equals int64 with a capital I. And again, let's set the second element to np.nan. This time, the series retains its int64 data type and doesn't get cast to float. In this case, a better way to set that value to nan is to use pd.na. You could also use the none keyword, but I'd probably opt for pd.na. Alright, now let's see how this works on a series of strings. So back in the day, if you wanted to build a series of strings, you could do something like gumbo equals pd.series open parens and then pass in a list of strings like A, B, and C. And then if you set the second value to np.nan and the third value to none, and then you print the series, it actually looks like this worked pretty well, but should it have? Notice the series has dtype object. What this means is we basically have a Python list. Each element of the series is actually just a pointer or a memory address pointing to some random location in your computer's memory that's storing the value of the element. This is bad because 1, it's inefficient for data access, and 2, it doesn't enforce a homogeneous data type constraint on our series. We're supposed to have a series of strings, but I set the second element to a floating point. Pandas 1.0.0 fixed both of these issues in one fell swoop with the string dtype extension type. So today we'd rebuild that series just like before, except we'd specify dtype equals string. And now if we set the second value to np.nan and the third value to none, our series would end up looking like this. If you're a little confused by this, don't worry, it's not that important for using pandas, and it's something you'll probably understand more over time. In any case, pandas provides 2 helper functions for identifying nan values. If you have a series X with some nan values like this one, you can use pd.isNA to check whether each value is nan, and pd.notNA to do the opposite. If you wanted to replace nan values with -1, You could do something like x.loc square brackets pd.isInAx equals -1, and this works, but Pandas provides a really convenient fill_in_a method that makes this even simpler. So instead, you could just do x.fill_in_a -1. Note that this returns a modified copy of x, so x doesn't actually get changed here. You can see if I print x, it hasn't changed. If you want the changes to stick, you can do the same thing and set the in-place parameter equal to true. It's also important to understand how nans work with boolean indexing. Suppose you have a series of values like this one called goo, and a corresponding series of boolean values called chew. What do you think goo.loc square brackets chew will return? In this case, we get value error, cannot mask with non-boolean array containing na/nan values. Notice that chew here is one of those pesky series with dtype object. In other words, it's a series of pointers. To fix this, we can rebuild chew specifying dtype equals boolean. And now when we do goo.loc square brackets chew, we get back 10 and 40. So the nan value in chew is essentially ignored. Keep in mind that the negation of nan is still nan. So if we do goo.loc square brackets negation chew, we only get back one row, not the 2 rows excluded in the previous subset. In this video, we'll learn about vectorization and why using natively built series methods is usually better than rolling your own custom methods. Suppose you have a series X with 1 million random uniform values between 1 and 2, and you want to calculate its mean. You're a confident, competent coder, so forget about using somebody else's code. You're going to write your own function to calculate the average. So you come up with something like this. You give it a whirl, only to find out it's slow as hell. By contrast, take a look at the built-in series method, mean. It's blazing fast. So why is the built-in method so much faster than your custom function? The answer is vectorization. It's important to understand that Python loops are slow. With each iteration of a Python loop, you're essentially giving your computer a new set of instructions to perform some task. So in this case, it's like you're giving your computer 1 million different sets of instructions. By contrast, the series.mean method is basically an alias for the NumPy mean method, which is vectorized. In this case, NumPy hands off the entire array of data to a lower level function in C with a single set of instructions for what to do. C then executes those instructions on the entire array, calculating the mean before handing the result back to Python. So to recap, Python loops are slow and you shouldn't use them except in some rare circumstances. Instead, opt for a vectorized solution using one of the many built-in Pandas and NumPy methods that implement fast algorithms using C. In this video, we'll see how you can use the apply method of a series to apply a function to each element in the series, and then we'll see why apply is usually inferior to a vectorized solution. Suppose you have a series called foo with 6 elements like this, and you want to apply some complicated function like this one to each element in the series. Here, myfunc takes in a scalar x and returns x minus 1 if x is even, otherwise it returns x plus 3. Okay, maybe this one-liner isn't that complicated, but for the sake of argument, pretend this function has hundreds of lines of cryptic code. In cases like this, you can use the apply method of the series object to apply myfunc to each element of foo. In this case, you'd say foo.apply and then pass in the function callable, myfunc, to get back a new series of values. We could even generalize myfunc by giving it some parameters, a and b, like this. And this time, we can call foo.apply myfunc and pass in trailing parameters for a and b. The apply method is great because it's easy to use and it generalizes well, but it's slow because it's not vectorized. If we apply myfunc to a series with 10 million values, it takes about 3 seconds to execute on Google Colab. By contrast, here's a NumPy-based solution that achieves the same thing in 258 milliseconds, roughly 13 times faster. With that said, the apply method is designed for convenience and code clarity, not speed. Keep in mind that sometimes myfunc might actually be a function imported from another package, or maybe it makes HTTP requests to some API, and so refactoring it into a vectorized solution just isn't feasible. In this video, we'll see when series operations create a copy and when they create a view. Suppose you have this series X. And then you set a new variable Y equal to X. Then you modify the first element of Y to be 99. Obviously this modifies Y, but you might be surprised to see it also modifies X. The reason this happens is because when we set Y equal to X, Pandas didn't make a copy of X, it merely made Y a reference to X. In other words, the variable Y points to the same block of data stored by X. This is known as assignment by reference, and some people would call Y a view of X. To avoid this, we can explicitly set Y equal to a copy of X using something like Y equals X.copy. Now, if we change Y, X is unchanged because Y points to a completely separate block of data. One of the reasons this is so confusing is because assignment by reference only happens under certain circumstances which aren't clearly documented and aren't always obvious. For example, if we have the series foo equals pd.series a, b, c, d, and we set bar equal to foo.log square brackets foo less than or equal to b, then we modify bar, setting the first element equal to z. Foo doesn't get changed, which means under the hood, Pandas copied the data in foo to create bar. Now, if we set baz equal to foo.ilog square brackets :2, which is the same exact subset we used when we built bar, except here we're using slicing, and then just like with bar, we set the first element of baz equal to z. This time, in addition to baz changing, foo also gets changed. As far as I can tell when it comes to series, if you assign a equal to b.log something, Pandas returns a copy, otherwise it returns a view. But this is undocumented and the rules change when we start using DataFrames, so I don't recommend memorizing any hard and fast rules. Instead, you kind of just have to play around with things. Use .copy to be safe, and just be aware of this quirky behavior. I know it sounds weird, but this is the kind of thing you get a feel for over time. Another situation where it's important to understand if Pandas is copying data is when it comes to pretty much any Pandas function that modifies a series. For example, every series has a method called replace, which basically lets you replace values with other values. So if you have a series of strings like this one called zoo, if you want to replace every instance of lion with hamster and every instance of tiger with bunny, you could do zoo.replace and then pass in a dictionary of old value, new value pairs. The result of this method is a copy of zoo with the replaced values. So we're not actually modifying zoo, we're just building a brand new series from it. If you wanted to update zoo with these replacements, you could just overwrite the variable like zoo equals zoo.replace, yada yada yada, which would work, but it'd be highly inefficient, since internally Pandas would create a whole new series, reassign zoo to it, and then delete the old series. To circumvent this, lots of Pandas functions have a parameter called inPlace, which, when true, tells Pandas to modify the data you're operating on rather than return a modified copy of the data. So if we wanted our replacements to stick, we could call zoo.replace just like before, except this time we'll set inPlace equals true. And now the data inside zoo actually gets updated with our replacements. In this video, we're going to do the first of many challenges. I tried to make these challenges align with what we've already learned, but in some cases, the solution requires a new function or trick that we haven't discussed. Now that's on purpose because in the real world, the problems you come across aren't limited to the things you've already seen. So part of being a good data scientist is having that ability to search for a solution online and to read and interpret documentation. So I'm going to encourage you to do all of those things in your attempt to solve these problems. All right, let's get started on the first challenge. You and your spouse have decided to let the internet name your next child. You've asked the great people of the web to submit their favorite names, and you've compiled their submissions into a series called Baby Names. Determine how many people voted for the following names: Chad, Ruger, and Zeltron. As they say, there's many ways to skin a cat, but here's the solution that I came up with. The key to my solution is to use the value counts method, which returns the frequency of each unique element in sorted order from most frequent to least frequent. So you can see babynames.valueCounts is a series whose index has the unique values of baby names and whose values are the corresponding frequencies. Since we want to get the frequency of Chad, Ruger, and Zeltron, we can chain babynames.valueCounts with .log, passing in a list of index values we want to select. In this case, Chad, Ruger, and Zeltron. Given two series, bees and knees, if the ith value of bees is nan, double the ith value inside knees. Here's the solution I came up with. Let's break it down. pd.isInAbees returns a boolean series indicating whether each element of bees is nan. .toNumPy then converts that series into a NumPy array. Piping that into knees.log selects the elements of knees where corresponding array values are true. And finally, *2 updates each element as 2 times itself. The tricky part of this problem is knowing how to avoid index alignment, and that you need to do it in the first place. If we didn't use the toNumPy method and left pd.isInAbees as a series, then knees.log would actually select elements of knees whose index matches the index of true elements in the series returned by pd.isInAbees. In other words, instead of picking out the corresponding values of knees by position, it picks out the corresponding values of knees by matching index label. After accidentally leaving an ice chest of fish and shrimp in your car for a week while you're on vacation, you're now in the market for a new vehicle. Your insurance didn't cover the loss, so you want to make sure you get a good deal on your new car. Given a series of car asking prices and another series of car fair prices, determine which cars for sale are a good deal. In other words, identify cars whose asking price is less than their fair price. The result should be a list of integer indices corresponding to the good deals and asking prices. Here's the solution I came up with. Let's break it down. Now in practice, I'd probably restructure this data and solve this problem with data frames, but since we haven't learned data frames yet, I've stuck to a series-based solution. So if we do asking prices minus fair prices, it actually uses the index labels to subtract the correct fair prices from each asking price. The problem with this is that the resulting series gets reordered by the index in alphabetical order, so we have to take another approach. My strategy here is basically For each asking price, get the corresponding fair price. To do that, we can say fairprices.loc and feed it the index labels from asking prices. We'll store that result in a variable called allFairPrices. Then we set off market prices equal to asking prices minus all fair prices. So the good deals are going to be the negative values in this series. Next, we set below fair prices equal to off market prices less than 0, which gives us a boolean series indicating whether each car for sale is below its fair price. We'll also chain that with .resetIndex drop equals true to make the index a range index like 0, 1, 2, 3, 4. So now our goal is to pick out the indices corresponding to true values, in this case 0 and 4. If we do below fairprices.loc square brackets below fair prices, we'll get back the subseries with just true elements. And then we can chain that with .index.toList to get back the index values in a list. You suspect your local grocery's been price gouging the ground beef. So you and some friends decide to track the price of ground beef every day for 10 days. You've compiled the data into a series called beef prices, whose index represents the day of each recording. Determine which day had the biggest price increase from the prior day. Note that the index of beef prices represents the day tracked, and it's not in order. Here's my solution. Let's break it down. The first thing I do is I use the sortIndex method to sort the series by its index. I use inPlace equals true to modify the data in place. Now we can interpret the first value of beef prices as the price of beef on the first day, the second value as the price on the second day, and so on. Since we want to get the day with the highest increase in price, we need a way to calculate the difference in price from one day to the next. In other words, we want to build a series where each element represents the change in price from the previous day. So if we had a series to represent the prior day's prices, then we could do beef prices minus prior day prices to get the daily price changes. We can accomplish this with shift. The shift method returns the values of a series offset by some amount. Using periods equals 1 means the ith value in the result will return the I minus 1th value in the original series. In other words, you can imagine the series shifting forward one step, which means we end up with the nan value at the front of the series, and we discard the value at the back of the series. Once we have beef prices and beef prices prev, we can subtract them to get the daily price changes, which we store in a variable called daily changes. Then we can use the series.indexMax method to pick out the index of the largest value in the series. You're organizing a competitive rock skipping league. 6 coaches and 20 players have signed up. Your job is to randomly and fairly determine the teams, assigning players to coaches. Keep in mind that some teams will have 3 players and some teams will have 4 players. Given a series of coaches and a series of players, create a series of random coach to player mappings. The resulting series should have coach names in its index and corresponding player names in its values. Here's the solution I came up with. Let's break it down. The first thing I do is I randomly sort the coaches and players using the .sample method with frac equals 1, which means randomly sample 100% of the series values. By default, this happens without replacement, so what we're doing here is essentially randomly shuffling each series. Next, my goal is to repeat the coaches series like this, until it's at least as long as the players series. Since there's 20 players and 6 coaches, with help from NumPy's seal method, I know I need to repeat coaches 4 times. I can do that by wrapping coaches inside a list and multiplying it by 4, which basically makes a new list with 4 elements, each of which is a reference to the coaches series. Then I can wrap that with pd.concat, which concatenates a sequence of series into a single series. Of course, this new series has 24 elements, which is a little bit longer than our player series, so we'll chain it with .head len players to pick out the first 20 values. Lastly, we'll copy the player series to a variable called result, and then set its index equal to the coach values we generated in the last step. In this video, we'll look at different ways to create a data frame from scratch. Perhaps the easiest way to make a data frame from scratch is to use the DataFrame constructor, passing in a dictionary of column name, column values, pairs. For example, here we build a data frame with 2 columns, name and age, and for each column we pass in a corresponding 3-element list of values. Let's pause for a second to talk about what exactly a data frame is. In short, a data frame is just a table of data with a row index. In this case, the row index is that unlabeled column of values on the far left. To be a little more pedantic, a data frame is a collection of identically sized series, all of which share the same index. Additionally, data frames have a column index for selecting and subsetting columns. We'll touch on that more later. Another way you can build a data frame is from a list of lists. In this case, each inner list represents a row, so you could build the same data frame as before using df equals pd.dataframe and then pass in a list of lists like this. Before we move on, let's talk about a few important tools for inspecting data frames. df.info is a great tool that basically reports everything you'd want to know about a data frame, including its size, index type, and column types. df.shape tells you how many rows and columns df has, just like NumPy does with a 2D array. df.axes returns the row and column indexes, and df.size tells you how many elements are in the data frame in total. In this case, if we wanted to change the column name age to years, we would do df.rename columns equals the dictionary age : years and set inplace equals true. In this video, we'll see how you can read from and write to CSV files with pandas. One of the most common ways to make a data frame is to load it from some pre-existing CSV file. Pandas has an awesome CSV reader for this, but before we use it, let's make a data frame from scratch and write it to a CSV so we have something to read. Here, I'll make a data frame called df with 3 columns and 1,000 rows. To write this data frame to a CSV, it's pretty simple. You just use the built-in dataframe.toCSV method and pass in a name for the file. For example, df.toCSV open parens open quotes pets.csv. By default, the file gets written to your current working directory, and if you don't know where that is, you can check it by importing OS and running os.getcwd. I'll also use os.listdir to list the contents of my current working directory. Alternatively, you can specify the file path you want to write the data to using the path or buff parameter. Also, by default, toCSV includes the row index in the output. So if you open the CSV file in the text editor, don't be surprised to find a nameless column at the front. For me, 9 times out of 10, I don't want this, and it's easy to prevent by setting index equals false. If you look at the documentation for toCSV, you'll find there's a ton of parameters that let you really customize the way a data frame is written to CSV. We won't go through them here since it would get boring fast, but they're pretty well documented, so I'll encourage you to peruse them on your own time. Now that we have a CSV file on disk, let's try loading it into a new data frame called pets. In this case, we'll use the global function pd.readCSV, passing in the name of the file. It might not seem that impressive, but if you've ever tried reading data from a file using a lower level language like C or C++, you should appreciate everything that's happening under the hood. Not only did Pandas recognize the column names, but it also interpreted the column data types correctly without any help from us. Of course, in the real world, things don't always go so smoothly. Sometimes you'll have to steer readCSV in the right direction using some parameters like sep to specify a value separator if your file is something other than comma delimited, header to tell Pandas if your file contains column names, index col to indicate which column, if any, should be used as the row index, and use calls to tell Pandas only read a certain subset of columns. Since readCSV has even more parameters than toCSV, we won't cover all of them either, but they're also well documented, so again, I'll encourage you to read through them yourself. In this video, we'll look at some basic indexing operations for subsetting and modifying data frames. This is really similar to indexing a series, so if you didn't see my lecture on indexing a series, you might want to go back and watch that one. To start, let's build a data frame called df with 6 rows and 3 columns. We can access an individual column in its series form using either square brackets with the column name passed in, like df square brackets open quotes shrimp, or dot notation like df.shrimp. Personally, I prefer to use dot notation, but sometimes column names include a space, in which case you're pretty much forced to use square bracket notation unless you rename your columns. So for example, you can do df square brackets open quotes red space fish, but not df dot red space fish. If you want to access multiple columns, you can do that too using a list of column names, like df square brackets and then pass in the list shrimp, crab, in which case you'll get back a data frame object whose data is a copy of the original data frame. If you want to pick out certain rows of a data frame by their position, you can do that using iloc, just like you can with a series. For example, if you want to get the first, third, and fifth rows of df, you could do df.iloc square brackets and then pass in the list of indices 0, 2, and 4. Or you could use slicing, like df.iloc square brackets 0:5:2, which means give me every row from index 0 inclusive up to index 5 exclusive, stepping by 2. If you want to pick out an individual row, like the second row, you might try something like df.iloc square brackets 1, which works, but returns the result as a series. In most cases, you probably want to get this back as a one-row data frame, and to do that, just wrap the 1 inside a list, like df.iloc square brackets list 1. You can also use iloc to subset columns, so you could do something like df.iloc square brackets colon, comma, list 0, 1 to get back columns 0 and 1. In English, you could describe this expression as saying, give me every row of the data frame, but only columns 0 and 1. And if you did df.iloc square brackets list 0, 2, comma, list 1, 2, it'd be like saying, give me rows 0 and 2 with columns 1 and 2. Now, as you probably guessed, just like iloc can be used to subset a data frame, so can loc. To make the distinction a little more clear, let's start by replacing df's index with the letters A through F. Now, if we want to pick out the rows with index labels B and E, we can do df.loc square brackets and then pass in the list B, E. We could combine row and column subsetting to pick out rows A, C, and F with columns crab and shrimp, like df.loc square brackets list A, C, F, comma, list crab shrimp. And we can even use slicing to pick out every row between B and E for column crab, like df.loc square brackets B:E, comma, list crab. Now, what if you wanted to pick out the first 3 rows with columns shrimp and redfish? This is one of those times where, frankly, Pandas is kind of disappointing, because what you really want to do is something like df.loc square brackets :3, comma list shrimp comma redfish. But this doesn't work because loc searches for index labels, so it doesn't know how to interpret the positional slicing :3. On the other hand, df.iloc square brackets :3, comma list shrimp redfish doesn't work because iloc uses positional indexing, so it doesn't know how to interpret the list of column names shrimp and redfish. Fortunately, there's a not so terrible workaround for this. The trick is to convert the column names shrimp and redfish to their corresponding positional indices 0 and 2, and then just use iloc as usual. Essentially, we want to do df.iloc square brackets :3, comma list 0, 2. But to allow for column names instead of column indices, we can replace 0, 2 with df.columns.get_loc open parens c for c in the list shrimp comma redfish. df.columns.getLoc returns the positional index of a column given its name. So we just combine that with a simple list comprehension to convert a list of column names to positional indices on the fly. I should also mention that df.columns returns the column index of the data frame, and in this case it's just like the row index, since our row index is also made up of strings. You can also apply boolean indexing to data frames just like you can with series. For example, if you wanted to get the rows of df where column shrimp is less than 40, you can start by building a boolean series like mask equals df.shrimp less than 40. If we print mask, notice it has the same index as our data frame. So then we can use this boolean series with df.loc to pick out the rows where shrimp is less than 40. More commonly, you'll see this as a one-liner like df.loc square brackets df.shrimp less than 40. And just like series, you can combine logical conditions to create more intricate filters like rows where shrimp is less than 50 and crab is not divisible by 10. In this video, we'll go over some basic data frame operations, like how to insert or delete columns and how to modify existing data. Inserting a new column into an existing data frame is easy. For example, if you have a data frame like this, you can insert a new column, C, using df square brackets open quotes C, and setting it equal to either a list, series, NumPy array, or a scalar. Note that you can't use dot notation to create a new column, so you can't do df.d equals 1. You have to use square brackets like df square brackets open quotes d equals 1. You can also combine columns to create a new column. For example, you could create column E as the sum of A and C, like df square brackets open quotes E equals df.a plus df.c. You can also create or update column values using boolean indexing. For example, we could update d to equal 0 where b is rabbit by doing df.loc square brackets df.b equals rabbit, comma f equals 0. Deleting columns is also pretty straightforward. If you wanted to delete columns A and C, just do df.drop open parens columns equals and then a list of column names like A and C, and then set inplace equals true to modify df. Just as series has an apply method for applying some function to each element in a series, DataFrame has an apply method that lets you apply a function to each row or column in a data frame. In this video, we'll see how and when to use it. We'll start by making a very simple 3-row, 2-column data frame called df. DataFrame's apply method has two primary arguments, func and axis. Func tells apply what function to use, and axis tells apply whether to apply the function along axis 0, the row axis, or along axis 1, the column axis. For example, if we call df.apply open parens func equals np.sum axis equals 0, we get back a 2-element series that's the result of calling np.sum on each column of df. If we do the same thing with axis equals 1, we get back a 3-element series that's the result of calling np.sum on each row of df. Now suppose we have a data frame called kids, like this one with mixed column types. And our goal is to determine whether each child should be allowed in a haunted house. The rules for getting in the house are, you have to be at least 12, or you need to have adult supervision. For tasks like these, apply works great. In this case, we'll start by making a function called isAllowed that inputs age, a number, and with adult, a boolean, and returns a boolean indicating whether the kid is allowed to enter the haunted house. Now we'll call kids.apply, passing in our function isAllowed and axis equals 1 because we want the function to be applied on a row-by-row basis. Of course, this won't work because we haven't told pandas what values for each row to use for the arguments of our function. In fact, it's not even clear what's being passed into our function. To understand apply with axis equals 1, let's pick out the first row of our data frame, which we can do with row_0 equals kids.iloc square brackets 0. What we get back is a series. Now, you might remember me saying you can't have a series of mixed types. So how do we have a series with a string, an int, and a boolean? The answer is we don't. We actually have a series of pointers, i.e. memory addresses. That's why the D type is reported as object, because even though every pointer in the series is technically just an integer, what it points to could be any type of object in memory. In any case, this series is exactly what the apply method uses for the function input. So let's modify our function to expect and operate on this type of input. And now the same kids.apply call we made earlier works. But let's not do that because it ruins a perfectly clean and generic isAllowed function. Instead, let's use a lambda function as a bridge between the series input and our original isAllowed function. We'll start by reverting our isAllowed function back to what it was. And then we'll say kids.apply and pass in lambda row : isAllowed parens row.loc age, row.loc with adult. In this case, we're using lambda as a wrapper for our isAllowed function. Tacking that onto our kids data frame, we can see exactly who's allowed in our haunted house and who's not. Sorry, Jimmy. As with series, when you work with data frames, it's important to be aware of when you're copying data and when you're referencing data. In this video, we'll see examples of both. To start, we'll make a simple data frame called df. Now let's create a variable v1 and set it equal to the series extracted from column x of df. If we modify v1, notice that df also gets modified. However, if we create another variable, v2, and we set it equal to column y plus 1, then if we modify v2, this time df doesn't change. Now let's set v1 equal to the first 2 rows of df using iloc with a list of indices. And let's set v2 equal to the first 2 rows of df using iloc with slicing. If we modify v1, Pandas throws up a warning telling us that we're modifying a copy of a slice of df. And indeed, when we inspect df after modifying v1, we see that it's unchanged because v1 really was a copy. On the other hand, if we modify v2, df also changes, which means v2 is just a view or reference of df. In other words, v2 is literally just pointing to df's data in memory. This example is particularly interesting because we get the same warning saying that we're modifying a copy of a slice from a data frame, but that's actually incorrect. In this case, v2 is a view, not a copy. Kind of annoyingly, this warning is known for throwing up false positives. Now, this behavior of assigning a view of df that has direct access to df's underlying data is actually pretty cool and can be handy in some scenarios. However, if it's not what you intended, it can cause all sorts of trouble, since sometimes you'll be modifying a view and not realize that you're also modifying the original data frame. To avoid this behavior, use DataFrame's .copy method to explicitly copy the underlying data, for example, like this. In this video, we'll look at one of the most common and important operations involving data frames, merging them together. To do this in Pandas, the workhorse function is merge. To motivate it, suppose we're doing some analysis for a veterinary office, and the office has two tables of data: pets, which has one row per pet, here the index represents each pet ID, and visits, which has one row per visit, where the index represents each visit ID. The merge function has four types of joins: left, right, outer, and inner, with the default being inner. The join type determines which keys show up in the result. Let's start with inner join. The result of an inner join only includes keys that exist in both the left and right tables, although a single key can appear multiple times in the result if it appears multiple times in one of the input tables. This makes more sense when you see it, so let's look at an inner join between pets and visits based on pet IDs. Here we call pd.merge and we designate pets as the left table, visits as the right table, the join type as inner, left index equals true because in the left table, i.e. the pets table, pet IDs are stored in the row index, and right on equals pet ID because in the right table, i.e. the visits table, pet IDs are stored in a column called pet ID. In other words, we want to join the row index in the left table to the pet ID column in the right table. Notice a couple things about the result. Pet ID 11 is excluded because it only existed in the pets table, and pet ID 31 is excluded because it only existed in the visits table. Also, pet ID 42 occurs 6 times in the result because it occurred 3 times in the visits table, each of which matched to 2 occurrences in the pets table. When your data frame's row index has some specific meaning, kind of like ours, it's a good practice to give it a name. So let's go ahead and rename the row index in pets to pet ID. And let's rename the row index in visits to visit ID. A convenient benefit to naming the pet ID index is that we can rebuild the inner join from before using on equals pet ID instead of setting left index equals true and right on equals pet ID. When you use the on keyword like this, Pandas searches both tables for matching column name and or row index to merge the tables with. Also notice that this result is slightly different than our previous version, specifically the resulting row index is different and the resulting column order is different. I'll touch on that a bit later. Now let's look at a left join. The result of a left join retains all and only the keys in the left table. Let's see it in action, again making pets the left table and visits the right table, and joining on pet ID. In this case, the left table, pets, includes pet ID 11, which doesn't have a matching record in the right table, visits, but the result still includes it. And for unmatched records like this one, Pandas fills in the columns from the right table with nan. Also note that pet ID 42 again expands into 6 resultant records. Next up is right join, which is exactly the same thing as a left join, just reversed. So if we do pd.merge left equals pets, right equals visits, how equals right, on equals pet ID, in this case pet ID 11 is excluded but pet ID 31 is retained in the result. The last type of join is an outer join, which includes every key from both tables in the output. Somewhat disappointing is the fact that Pandas doesn't have a native anti-join, which basically answers the question, what records from table A don't match any records from table B? But there's a couple ways we can cook this up. Suppose we want to see what records in the pets table don't have a matching record in the visits table via pet ID. We can start by doing an outer join with indicator equals true. That'll produce an output like this, where the column _merge indicates that the resulting record came from the left table, the right table, or both. From there, it's pretty obvious how to get the records in pets, not in visits. Just filter the result where _merge is left only. The nice thing about this is that it's simple. The downside is that it's extremely memory inefficient. We're unnecessarily creating this big intermediate table before we filter down to the one row that we care about. So the second method for implementing an anti-join is a little trickier, but it's more memory efficient. The basic idea is, for each pet ID in the pets table, we check if it exists in the visits table using the isin method. Then we negate the result and use that to subset the pets table. So if we do pets.index.isin, open parens visits.petid, we get back a boolean array indicating whether each pet ID in the pets table also exists in the visits table. Then we can negate that array and use it as a boolean index to subset the pets table. Since the visits table includes duplicate pet IDs, we can slightly improve this by using only its unique pet IDs. Before I close out this lecture, I want to briefly mention a few things. First off, if you want to join data frames using multiple columns, you can do that too just by passing in a list of column names. Secondly, if you join two tables A and B using A's index and a column from B, the resulting data frame will inherit its index from B. If you join on columns from both tables, the resulting data frame will create a brand new row index. Lastly, let's say you left join table B onto table A, meaning A is the left table and B is the right table. The rows in the result will be ordered by first when they occurred in A, and second when they occurred in B. Here's an example that shows what I'm talking about. You can see how the rows in A never swap positions, nor do the rows in B with the same key. The kicker is that this behavior isn't documented, so while it can be useful in some situations, you might not want to rely on it. I asked about this on GitHub, and kind of frustratingly, no one got back to me. Also, this behavior doesn't work for right joins, which some people have already classified as a bug, and is supposed to be fixed soon, hopefully by the time you're watching this video. In this video, we'll see how you can aggregate the rows of a data frame to calculate summary statistics. For example, suppose we have a data frame with two columns of floats, x and y, and we want to calculate the sum of each column. To aggregate it, we just need to call df.ag and then pass in the name of an aggregation function like sum in quotation marks, or we could pass in a function callable like np.sum. When you pass in a string like open quotes foo_func, Pandas first looks for a data frame method called foo_func. If it can't find anything, then it looks for a NumPy function called foo_func, and if it still can't find anything, it raises an error. If you define your own function named foo_func like this, you can use it with ag, but you have to pass it in as a callable, not as a string. Alright, so when we did df.ag, open parens, open quotes sum, we got back a 2-element series with the sum of each column. If we want to get back the result as a data frame, we could wrap the aggregation function inside a list, like df.ag, open parens, list, open quotes sum. Using a list, we can aggregate the data using multiple functions. For example, to get the sum and mean of each column, we could say df.ag open parens list sum mean. Now, what if we wanted to calculate the sum and mean of column X and the min and max of column Y? In this case, we can use a dictionary of column to list of functions pairs to tell pandas exactly what functions to apply to each column. In this case, we could say df.ag open parens dict x colon sum mean y colon min max. This might be obvious, but we should note that aggregation is intended to be used with a special class of functions that take in a series of values and reduces them down to a single value, or at least fewer values than the input. These could be things like sum, mean, min, or max. By contrast, transformation functions like sort, fill in A, and round take in a series of values and return another series the same length as the input. So you shouldn't use these functions to aggregate a data frame. Looking at the docs for dataframe.ag, you'll notice there's an axis argument. By default, it's set to 0, so when we do something like df.ag open parens min, pandas calculates the min value across axis 0. In other words, aggregating the rows of the data frame. If we wanted to, we could do df.ag open parens min axis equals 1 to aggregate the columns, calculating the min value in each row. Also notice the star args and star quargs parameters. So if you define some custom function like inth underscore value that returns the nth value of a series, you could aggregate df picking out the third value in each column using df.ag open parens nth value, comma n equals 3. By the way, for simple functions like this, you'll often see people build them on the fly using lambda, like df.ag open parens func equals lambda x comma n colon x.ilog square brackets n comma n equals 3. In this video, we'll see how you can use groupby to partition a data frame into groups and subsequently aggregate or transform the data in each group. To start, let's build a data frame with 4 columns, A, B, C, and D. By the way, .convert dtypes is a handy way to make sure we're using Pandas' modern string and integer data types, which allow for NaN values. Without it, A would be type object, and D would be type float64. Every groupby operation starts with a call to the groupby method. Perhaps the most important parameter of groupby is the by argument, which tells Pandas how you want to split the data frame into groups. Usually you'll specify one or more column names here. For example, df.groupby open parens by equals A tells Pandas you want to partition the data based on unique values in the column A. In this case, Pandas partitions the data into 2 groups like this. Alternatively, you could do df.groupby open parens by equals list A comma B to partition the rows based on the set of unique A-B pairs. In this case, Pandas partitions the data into these 3 groups. The result of calling df.groupby is a special type of object called a DataFrame groupby. Now, I should note that you can also call groupby on a series, in which case you'd get back a series groupby object. DataFrame groupby and series groupby are both extensions of a generic groupby class, so they behave very similarly. Groupby objects have some special features and attributes like .groups, which returns a dictionary of group key colon list of input rows pairs. For example, if we set groups underscore AB equals df.groupby open parens list A comma B, then groups underscore AB dot groups tells us that rows 0 and 2 correspond to the key foo comma false. Similarly, groups underscore AB dot ingroup tells us the numeric group ID associated with each row of the input data. Notice that these group IDs are ordered by the order of their keys. For example, group 0 corresponds to the key bar comma true, because alphabetically bar comes before foo. But in the original data frame, the key foo, false is the first one to occur. So if you'd rather have the groups ordered by the first occurrence of each key, you can do so by setting sort equals false inside the call to groupby. For example, if we set groups underscore AB equal to df.groupby open parens by equals list A, B, sort equals false, and then we call groups underscore AB.inGroup, you can see group 0 occurs before group 1, which occurs before group 2. Another thing we can do is, instead of passing a list of column names into the by argument of groupby, we can pass in a series, in which case the series values determine the groups, and the series index determines which rows of the data frame map to each group. For example, if we want to group the data based on the whole part of the values in column C, we could say holes equals df.c.apply open parens np.floor, which returns a series, and then df.groupby open parens holes. In this case, the values in the series get partitioned into 5 groups. Then the index labels of the series tell pandas how to map the rows of df into those 5 groups. Index 0 goes to group 1, index 1 goes to group 0, index 2 goes to group 2, and so on. Note that typically this would be written as a one-liner like this. Partitioning data into groups isn't all that useful until you actually do something with the groups. Usually after you group some data, you follow it up by aggregating the groups or transforming them. Let's start by looking at some groupby aggregate methods. We've already seen how to aggregate an entire data frame down to one row. Aggregating a groupby object is essentially the same thing, where the aggregation applies to each group of data, and then the results are combined into a data frame or series. The best way to get a feel for how this works is to do some examples. Let's start by grouping df by column A, and then aggregate the groups taking the sum of column C. One way we could do this is df.groupby open parens open quotes A, square brackets open quotes C, dot sum. Alright, let's break that down. df.groupby open parens A creates a data frame groupby object. Tacking on square brackets C isolates column C, returning a series groupby object. Now keep in mind data frame groupby and series groupby are both derived from a generic groupby class. So if we look at the documentation for groupby, we can see that it includes a sum method for taking group sums, which is what we do here. The result is a series whose index labels are the group keys and whose values are the group sums. Here's a similar operation, except here we wrap C inside of a list. In this case, Pandas doesn't convert the DataFrame groupby object into a series groupby object when we pick out column C, and as a result, we get back a data frame of group sums instead of a series of group sums. This is analogous to doing df square brackets open quotes C, which returns a series, and df square brackets list C, which returns a data frame. We could also use this technique to calculate group sums for multiple columns. For example, df.groupby open parens A, square brackets list C, D, dot sum returns a data frame with sums over D and C aggregated by unique groups in A. We could also replace .sum here with .ag and pass in a method name or function callable. Basically, everything we learned when we covered data frame aggregation can be applied here, which means you can even do things like this to get the sum of C and the mean and variance of D for each group in A. Note that the resulting data frame here has something called a multi-index for its columns. Similarly, if we did df.groupby open parens by equals list A, B, square brackets list D dot mean, we'd get back a data frame with a row multi-index. We'll cover multi-indexes in a future video, but for now just know they exist. If we group by B and D, taking the min and max of C, you'll notice that Pandas ignores and drops the nans inside D. Personally, I think this is a really unfortunate default behavior, but you can turn it off by setting drop NA equals false within the call to groupby. Another question that comes up a lot is how do you rename the output columns? So let's say you wanted to do the same thing as before, but you want the output columns to have names C_min and C_max. In this case, you can pass named tuples into the agg method like this, where the keywords become the column names. Now let's look at some groupby transform operations. For example, suppose you want to sort the values in column C, but only relative to each group in A. One way we can do this is df.groupby open parens A square bracket C dot transform open parens lambda x colon x dot sort values. Let's break that down. df.groupby open parens A square brackets C groups the data by column A and then isolates column C. Next comes the .transform bit. The transform method takes one primary argument, which is the function you want to apply. In this case, sort values isn't a built-in groupby method, so we have to pass it in as a function callable. Here we've done it using lambda, a useful construct because you can use lambdas to make all sorts of custom functions on the fly. But we could actually just reference the sort values function directly from the series module. The result of this operation is a new series whose index matches the row index of the original data frame. This is useful, for example, if you want to tack this on as a new column of df, or overwrite the existing values in column C. For example, if we add this as a new column called C_sorted_within_A, you can see how the new values compare to the old values. Now, as you probably guessed, if we do the same exact thing but we wrap C inside a list, we get back a DataFrame with essentially the same exact data. Let's look at another example where again we group by column A, but this time we calculate the mean of columns C and D. Like before, df.groupbyA creates a DataFrame groupby object. Then we pick out columns C and D, giving us a slightly different DataFrame groupby object. And then we call .transform, passing in mean, which we can do because mean is one of the built-in groupby methods. And at this point, you might expect the result to have fewer rows than the input, because mean is an aggregation function. But to the contrary, the result is a data frame with the same number of rows as df. And this is the important thing to understand about the transform function. The output rows will always match the input rows, and this is in stark contrast to the agg function, in which the output row count is usually much less than the input row count. In this case, the mean of each group in A was broadcast to match the length of the original data frame, which is why you see a bunch of repeated values in the output. Suppose we've polled 5 couples on their hobbies. For each couple, determine what hobbies the man has that the woman doesn't have, and what hobbies the woman has that the man doesn't have. Here's my solution. Let's break it down. The key to this solution is to make use of Python's set data structure and its ability to efficiently calculate the difference between two sets. For example, if you have two sets x and y, then x minus y returns a set with the elements in x not in y, and y minus x returns a set with the elements in y not in x. In order to make use of sets for this problem, the first thing we need to do is convert the elements of couples from lists to sets. Apply map works well here as it applies some function to each element of the data frame. In this case, the function is simply set, since set open parens x converts a list x into a set. Now let's compute the hobbies that each woman has that her man doesn't have. We can do that as follows. Let's break it down. Each data frame has a flexible .diff method that calculates the difference between elements. By specifying axis equals 1, we're telling pandas to calculate the difference between elements in each row. And by specifying periods equals 1, we're telling pandas for each element in some row, subtract the element one position behind it. In this case, the result is a data frame where the man column is full of nans and the woman column contains the set difference for woman hobbies minus man hobbies, which tells us what hobbies each woman has that her man doesn't have. The last thing we need to do is just drop the man column. Then we can repeat the same thing for each man. The only difference is that when we call sets.diff, we need to set periods equals -1 to subtract each element one position from the right instead of one position from the left. And then to get our desired output format, we combine the data frames with pd.concat and reuse apply map to convert the sets to lists. Whenever your friends John and Judy visit you together, y'all have a party. Given a data frame with 10 rows representing the next 10 days of your schedule and whether John and Judy are scheduled to make an appearance, insert a new column called days till party that indicates how many days until the next party relative to each day. Days till party should be 0 on days where a party occurs, 1 on days where a party doesn't occur but will occur the next day, and so on. Here's the solution I came up with. Let's break it down. The first step is to build a series that indicates whether each day is a party. Next, I reverse the series and then call CumSum, which calculates the cumulative sum of the values, keeping in mind that true is synonymous with the value 1 and false is synonymous with the value 0. This has the effect of grouping indexes or days together which look forward to the same party. For example, days 1, 2, 3, 4, and 5 all have ID 1 because they're all associated with the same party that occurs on day 5. Next, party.groupby open parens groups partitions the data in the party series based on unique values in groups and maps them back to the party series based on matching index labels. For example, index labels 9, 8, 7, and 6 are going to get grouped together. Index labels 5, 4, 3, 2, and 1 are going to get grouped together, and index label 0 is going to get grouped on its own. Then the CumCount method simply counts the elements in each group, like 0, 1, 2, 3, 0, 1, 2, 3, 4, and so on, except I use ascending equals false to count backwards. And that's going to give us the days until the next party. You can see it if we tack that on to the original data frame. The only issue is that after the last known party, we really should have NAs. So if we pick out the index of the last known party, which we can do with party.log square brackets party .index square brackets -1, then we can set everything after that index equal to NA. You own a collection of vending machines and you want to evaluate your inventory. Given a data frame of machine product stock, determine the number of machines carrying each product and how many of them are out of stock. In other words, build a new data frame with product as the row index and calculated columns in machines and in machines empty. Here's the solution I came up with. The first thing I do is build a count0 function that takes a series and counts the number of elements which are 0. Then I group the data frame by product and use .ag with some named tuples to count the number of rows in each group, i.e. the number of machines carrying each product, and to count the number of machines out of stock for each product. Given a data frame of married couples and a separate data frame with each person's age, identify cradle robbers, people who are at least 20 years older than their spouse and whose spouse is under the age of 30. Here's the solution I came up with. Let's break it down. The first thing I do is convert ages from a data frame to a series of ages indexed by the name of each person. Then I call ages.loc square brackets couples.person1 to get the age of each person 1. I want to insert that as a column in the couples data frame called age1, so I do couples square brackets open quotes age1 equals ages.loc square brackets couples.person1 dot to NumPy. Now, if we didn't use dot to NumPy, which converts this series into a NumPy array, Pandas would try to use index alignment, inserting values from the right-hand side into the left-hand side using matching index labels, which isn't what we want. So then I do essentially the same thing to get the age of each person too. And then I do some basic boolean filtering to identify cases where person 1 is a cradle robber and cases where person 2 is a cradle robber. Lastly, I use pd.concat to concatenate those series together and identify Adam and Rachel as the cradle robbers. Fed up with your city's roads, you go around collecting data on potholes in your area. Due to an unfortunate coffee spill, you lost bits and pieces of your data. So, given your data frame of pothole measurements, discard rows where more than half the values are nan. Otherwise, impute nans with the average value per column, unless the column is non-numeric, in which case use the mode. Here's the solution I came up with. Let's break it down. Data frames have an isNull method that checks if each element is null. In this case, potholes.isNull returns a data frame with the same shape as potholes, full of boolean values indicating whether each element is null. If we chain that with .sum axis equals 1, we get back the sum of true values, i.e. null values, in each row. If we compare that to half the number of columns in the data frame, it'll tell us which rows we need to drop. But before we drop those rows, we should use the data they have to help us fill in nans in other locations. Now, potholes.mean returns a series with the average value excluding nans in each numeric column, which we can use in conjunction with potholes.fillInA to fill in missing values. Next, we fill in missing values for the location column. Potholes.location.mode gives us the mode of location, so we pass that into potholes.location.fillInA with inPlace equals true. The only problem is that potholes.location.mode returns a series, and when you pass a series into fillInA, Pandas uses index alignment to map the fill values into the original series based on matching index labels. To get around this, we chain potholes.location.mode with .iat square brackets 0 to pick out the first value in the mode series, which in turn fills all the nans in the location column. Lastly, we get rid of rows we're supposed to exclude via potholes.loc square brackets negation drop rows, because we want to retain rows where the value in drop rows is false. And now we have a nice clean data set we can present to our city council. Earlier in the course, I said a pandas series is like a souped up version of a NumPy 1D array. Perhaps the best example of this is when you're dealing with a series of strings. In this video, we'll look at pandas methods for processing a series of strings. Let's start by building a series of strings that we'll call Cajun. Keep in mind, we're setting dtype equals string here to tell pandas we want to use the string dtype extension, which allows for nan values and forces the elements to be of type string. Now, the .str accessor of a series of strings gives us back a string methods object from which we can call each of the string processing methods. These methods are pretty simple and self-explanatory, so in this case the challenge is more about knowing what methods exist rather than knowing how they work. So in this lecture, we're just going to speed through a bunch of string methods, and if something piques your interest, you can pause the video and do some more research on your own. So without further ado, we can use upper to get back a series of uppercase strings, and lower to get back a series of lowercase strings. We can use len to get the number of characters in each string. We can use split to split each string along some specified delimiter and put the resulting substrings in a list. Chaining that with .str.get lets us pick out the ith substring in each list. We can use replace to replace part of a string with another string. For example, here we replace all spaces with dashes. By default, replace assumes you're passing in a regular expression, but you can turn that off with regex equals false. If you don't know what a regular expression is, it's basically a universally used syntax that lets you do advanced string matching. It's well worth learning, but it's beyond the scope of this course. We can use cat to concatenate the strings together using some specified separator, or we can just use cat to concatenate a series of strings with another same-sized series or list of strings. You can use string indexing to pick out a certain character or group of characters by position. For example, here we pick out the first character in each string. Here we pick out characters up to but excluding the third character. And here we pick out the last character in each string. We can use starts with to check if each string starts with the letter P, or ends with to check if each string ends with the letter S. We can use contains to check whether each string contains some other string or regular expression. We can use extract, which extracts the first matching substring using a regular expression with at least one capture group. For example, here we extract the first word that starts with a capital letter. Or we can use extract all to do the same thing, except it returns every matching substring. Of course, the output's in a slightly different format. If you don't know regular expressions, this is probably pretty cryptic, but if you do know them, hopefully you see how incredibly useful this is. Also, if you want to insert a prefix or suffix to each element in the series, you can do that simply by adding a string prefix or string suffix directly to the series, for example, like this. Inevitably, at some point you'll need to work with dates and times. Pandas helps ease the pain, but due to the hundreds of date and time formats, time zones, daylight saving, leap years, and even leap seconds, dates and times can be a frustrating beast. In this video, we'll do our best to tackle that beast, although we're not going to cover everything because doing so would take hours. Alright, we're about to go on a journey together, so grab a cup of coffee and buckle up. Real quick, for this video, I'm using Google Colab connected to a local Python runtime, version 3.9.1. Unfortunately, at the time of recording this video, Colab is stuck on Python 3.6.9, and some of the features in this lecture require version 3.9 and up. So keep that in mind if you're following along on Google Colab. The first thing we need to discuss are time zones. So when I was writing this script, I was sitting in Mandeville, Louisiana, and it was Thursday, December 10th, 2020 at 7:45 p.m., keeping in mind that I was in the US Central Time Zone. If at the same point in time, my friend in Melbourne looked at his clock, he'd say it was December 11th at 12:45 p.m. because he's located in the Australia-Melbourne time zone. If you look at a map of time zones, you can see how jagged and ununiform they are. Not to mention, there's a lot of historical messiness, like Russia going from 11 time zones to 9 time zones, then back to 11, and Nepal not even adopting a standard time zone until 1986. Nonetheless, suppose you were building a software application where people can schedule and share meetings. how would you store the date time each meeting is scheduled to start? Well, a logical thing to do would be to store the data relative to a single time zone, and then make your users, or basically the display of your application, responsible for converting those date times into their respective local time zones. For example, let's suppose you decide to use US Eastern as your master key time zone, from which all other time zones are referenced. Then if I schedule a meeting for 10:30 a.m. of May 1st, 2030 US Central Time, then under the hood, your calendar application would convert that to 11:30 a.m. of May 1st, 2030 and store that value into your database of all calendar events. Note that you don't even need to store the time zone, because you know that every time in your database is in US Eastern Time. Now, if I invite my Aussie friend to join my meeting, he can do a quick conversion to figure out that the meeting starts at 1:30 a.m. of May 2nd, 2030 local Melbourne time. This is a nice architecture because you've made storing date times very simple, and you've decoupled the hard work of actually converting between time zones to the end users. There's just one little problem. Like most states in the US and many countries around the world, New York observes daylight saving time, which means the clock rolls forward an hour in the spring and rolls backward an hour in the fall. Now, I think most people know this, but they don't really know this. I mean, how and when does the clock actually roll forward and backward? It happens so early in the morning that you've probably never witnessed it. Assume you're in New York. The date is Sunday, March 14th, 2021 at 1 a.m. If you actually stare at a digital clock, this is what you'll see. Did you catch that? The clock went from 1:59 a.m. back to 1 a.m., which means the times in the middle actually occurred twice on this date. This is a fatal flaw in your calendar software. Remember, you were storing data in US Eastern Time. So let's say someone scheduled a meeting that your software logged for March 14th, 2021 at 1:30 a.m. When is that meeting supposed to occur? The first occurrence of 1:30 a.m. or the second occurrence of 1:30 a.m.? The solution to this problem? Pick a better time zone for which to store your data. Specifically, pick Coordinated Universal Time, aka UTC, aka Greenwich Mean Time. This is the golden child of time zones. It does not observe daylight saving, it has never observed daylight saving, it is not going to observe daylight saving, it is the time zone which all of the world agrees to measure relative to. Now, if we're going to pass around times relative to UTC, it can be useful to have a standard format for doing so. One such format that you've probably seen is ISO 8601. For example, this is in ISO 8601, and in English it means June 1st, 2000 at 12 p.m., 5 hours behind UTC, meaning at that same instance in time it was 5 p.m. in UTC. So whenever you see a date time like this, with all zeros after the dash, it's safe to assume you're looking at UTC time. A somewhat strange but common alternative is to use a capital Z in place of the UTC offset, like this. Also note that you can kind of infer where an ISO datetime is based on the UTC offset, but it's not perfect because something like 5 hours behind UTC could refer to Chicago during daylight saving time, or New York during standard time, or Bogota, Colombia on any day, because Bogota doesn't observe daylight saving. Alright, now that we got that out of the way, let's talk about Python. We're going to cover 3 datetime packages / modules, and they're all interrelated. The first is Python's datetime module, the second is NumPy, and the third is Pandas. Let's start with Python's datetime module, which is probably the most widely used datetime library amongst Python developers. And we're not going to cover everything because this course is about pandas, but we are going to cover a few really fundamental concepts. The best way to import the module is a slight point of contention between developers, but I like to import datetime as DT. With datetime, you can make a date like dt.date open parens year, month, day. Now, dates are always time zone naive, which means they don't know anything about time zones, they're just dates. So what about date times? Well, you can make a time zone naive datetime like dt.datetime, open parens, year, comma, month, comma, day, comma, hour, comma, minute, comma, second. Or dt.datetime.striptime, open parens, and then pass in a string like this, and a format string like this. StripTime is a universal format for parsing dates and times from strings. Here I'm telling Python the first portion of this string is the month, followed by a slash, followed by the day, followed by a slash, followed by a 4-digit year, followed by a space, followed by a 12-unit hour, followed by AM or PM. If you're wondering how I knew what format codes to use, the docs for datetime include this really handy reference table. You can also make time zone aware datetimes like dt.datetime.from ISO format and then pass in a valid ISO 8601 string. Or we can import the zone info module and then do dt.datetime.striptime just like before, and then chain that with .replace, open parens, tzinfo equals zone info, passing in a valid geographic time zone name. By the way, a fantastic reference for time zone names is this Wikipedia article titled List of TZ Database Time Zones. Now that we have some date times, we can use the time delta class to add 24 hours to each date time. For example, if we add 24 hours to dt-naive1, unsurprisingly, we get back January 2nd at 8:15 a.m. and 20 seconds. Watch what happens if we add 24 hours to dt-aware1 and dt-aware2. In both cases, we get back November 7th, 2021 at 12 p.m. The issue with this is that if you're in New York 24 hours after 12 p.m. on November 6, 2021, the clock's actually going to read 11 a.m., not 12 p.m., because daylight saving ended and the clock rolled back an hour. This information is embedded in .tzinfo.dst. So if you do dtaware2.tzinfo.dst open parens dtaware2, it tells you that the daylight saving adjusted time is 1 hour behind what's actually being reported. However, when we call dtaware1.tzinfo.dst open parens dtaware1, we get back nothing. This brings up an important distinction between ISO UTC offset and geographic time zones. When you think about the date time 2021, November 6, 12 p.m. minus 500, that's a perfectly valid representation of a daytime in New York, which observes daylight saving. But it's also a perfectly valid representation of a daytime in Bogota, Colombia, which doesn't observe daylight saving. So there's really no reason for Python to assume that this daytime is being used somewhere that observes daylight saving versus somewhere that doesn't. So if you want your daytimes to be daylight saving aware, make sure that you use actual geographic time zones and not UTC offsets. Next up, we have NumPy. Things are a little simpler in NumPy. For one, there's no date type, only a date time type. Two, NumPy datetimes are time zone naive, meaning there's no support for time zones in NumPy. There was, but it was actually deprecated in version 1.11.0. So if you want to make a datetime in NumPy, you could do import NumPy as np, np.datetime64 open parens, and then pass in a datetime like this. Or if you want to make an array of datetimes, you could do np.array, then pass in a list of datetime strings and set dtype equals datetime64. So how are these datetimes represented internally? Well, datetime64 is really just a wrapper for int64. In fact, we can add an integer to a datetime64. For example, if we add 1 to this datetime, we get back a new datetime that's 1 minute ahead of the original datetime. And if we add 1 to this array of datetimes, we get back new datetimes which are 1 millisecond ahead of the original datetimes. This brings up an important concept, which is that the datetime64 data type in NumPy has an associated unit that determines the step size between sequential date times. For example, if we call np.dtype on the first date time, you can see that the associated unit is m, which stands for minutes, which is why when we add 1 to it, we jump by a minute. If we explicitly set the unit as seconds, like this, then when we add 1, we jump by a second. Now keep in mind, datetime 64 is 64 bits, which means it can represent 2 to the 64th, or about 18 million trillion different datetimes. Which datetimes, you ask? Well, it's the 9 million trillion datetimes before and after January 1st, 1970 UTC. So if we make an array of datetimes and set our unit to seconds, it means we could have datetimes that range from about 290 million years before 1970 up to 290 million years after 1970. If our unit was nanoseconds, we could only have datetimes that range from about 292 years before 1970 up to 292 years after 1970. And if you tried to create a datetime outside of that range, NumPy would convert it to something totally different. By the way, when you have datetimes centered around January 1st, 1970 UTC, it's known as Unix time or POSIX time. Also, NumPy reserves one of those bits for NAT, or not a time, so you can represent missing or invalid values like this. Oh, and notice the unit here is day, so even though there's no date type in NumPy, we can kind of represent dates using datetimes with daily units. Alas, we get to pandas. The workhorse datetime type in pandas is timestamp, which is really just a wrapper for NumPy's datetime 64 type. Similar to NumPy, pandas doesn't have a proper date type, so if you want to represent a date like January 3rd, 2001, you'd typically use the timestamp January 3rd, 2001, hour 0, minute 0, second 0. There's also something called a period type, but we're not going to cover it because it's seldom used, especially compared to timestamps. Now, the workhorse function to create a timestamp is the toDatetime function, where you usually pass in a string like this. Note that unlike NumPy, Pandas timestamps are always stored with nanosecond units, so you can't create a timestamp before 1678 or after 2262. If you try it, you'll get an error. Also, unlike NumPy, Pandas timestamps can be timezone aware. If you want to create a timestamp like March 8th, 2001 at 3 p.m. US Pacific time zone, you could do something like this. By the way, notice how the toDatetime function smartly interpreted our datetime string without us telling it how. Cool, although it's better to be explicit about the format, which you can do by passing in a strip-time format using the format parameter, in this case like this. So the timezone information is stored in the .tz attribute of the timestamp. And if you want to change the timezone, you can use the tzconvert method like this. If we pass a list of datetime strings into the toDatetime function, we get back a datetime index that we could use as the index of a series or a data frame. If we wrap that with pd.series, we get back a series of datetime 64s. Now let's say we wanted to add 12 hours to each of those datetimes. If we assign that series to a variable x, then we could do x plus pd.timeDelta, open parens, value equals 12, unit equals capital H. So if you want to add or subtract time from a series of datetimes, you have to do so using an instance of timeDelta, specifying a value and a unit. By the way, if you subtract two timestamps like this, what you get back is a timeDelta. Sometimes you'll want to build a sequence of datetimes based on a regular interval. For example, you can make a datetime index with 10 values starting on March 8th, 2020, iterating by 12 hours using the dateRange function. If we did the same thing, but with tz equals America/Denver, Notice the output changes slightly because daylight saving in Denver started at 2 a.m. on March 8th in 2020, meaning the clock in Denver went from 1:59 a.m. to 3 a.m., basically skipping the whole 2 o'clock hour. Let's go ahead and use this datetime index as the index of a series of stock prices. One of the neat things about this datetime index is that we can index the series in some simple but powerful ways. If we say foostock.loc, open square brackets, open quotes, 2020-03-09, we actually get back both records that happened on March 9th. If we did foostock.loc, open square brackets, open quotes, 2020-03, we'd get back every record that happened in March. If we passed in a particular timestamp, we could pick out a single value from the series, like the value on March 9th at 1 a.m. And we could even select a slice of values with something like this. So that's about all we're going to cover on dates and times in Python. There's actually a lot of stuff we didn't cover, but I think we hit all the fundamental things. It's no secret that the real key to learning this stuff is to practice using it, so check out my challenge problems to get started. One of my favorite features of Pandas is its ability to represent categorical data using the categorical type, much like the factor data type in R. In this video, we'll see how categoricals work and when you should use them. A categorical takes on a limited and usually fixed number of possible values, i.e. categories. To motivate this data structure, suppose we have 4 cars, and for each car we have its VIN number, color, and size classification. Our goal is to store each set of data using pandas. Now, VIN numbers are unique identifiers for cars, so we actually don't want to use the categorical data type to store VIN numbers because each VIN number is unique to a single car. In other words, VIN numbers aren't categories, they're unique identifiers. So in this case, it'd be better to store them using a plain old series of strings. In the case of colors, this is a classic candidate for categorical data, since we have a limited selection of colors, and each color sort of represents a collection of different cars. We can build a categorical easily using the pd.categorical function, very similar to the pd.series function. If we print the categorical, we can see the values and the unique categories, blue, green, and red. Note that this is not a series, but you could make it a series just by wrapping it in pd.series. By default, when you build a categorical, Pandas sets the categories as the unique non-nan values in the data. But if you want to set the categories explicitly, you can do so using the categories argument. This is especially useful if, for example, your website or dealership supports more colors than the cars you have in stock. So you could build a categorical like the last one with the additional categories black, orange, and yellow. The categories parameter is also useful because it lets you organize the order in which categories should be displayed, which could be handy for things like plots or reports. Without specifying the categories parameter, Pandas displays them in lexical order, which basically means A to Z. But maybe you want to report them in a different order, like bright to dark, in which case you can build the categorical like this. Now let's talk about car sizes. This is another good candidate for using the categorical data type. It's a lot like colors, but with one key difference. Car sizes have an inherent order, whereas colors don't. Now, I did say that you could order the color categories to your liking for reporting or display purposes, but in no means did I imply that the colors themselves have an inherent order. Orange is not more or less than black. Blue is not before or after yellow, and so on. By contrast, sizes have an inherent order. So when we build a categorical, we'll want to specify the categories in the correct order, and set the ordered parameter to true. Now when we print sizes, you'll notice that the categories are reported with less than symbols, indicating that they have a meaningful order. This is really cool because it means you can do things like compare sizes less than extended and get back a boolean array. Now it's important to note that categoricals don't have .loc or .iloc accessors, so if you wanted to subset sizes as those less than extended, you'd have to do it using basic square bracket notation like a NumPy array. Although you could create a series with a categorical index like this. In which case you could do something like sizes series.loc open square brackets open quotes mini. Another really cool benefit to using categoricals is that you can one-hot encode them using Pandas getDummies function. For example, if you call pd.getDummies on sizes, you get back a corresponding 4-row data frame of zeros and ones, where ones indicate the size corresponding to each row. If you're not familiar with this format, it's a really common input structure for a bunch of machine learning models. We've seen earlier that when you group by and aggregate a data frame on multiple columns, you get back a new data frame with a multi-index. A multi-index or a hierarchical index is exactly what it sounds like. It's an index that uses multiple values in its keys. In this video, we'll see how multi-indexes can be useful and how to use them. Let's make an example dataset of store product pairs. There's a few ways you can make a multi-index from scratch, but in my opinion, the most intuitive way is to use the pd.multiindex.fromTuples constructor, passing in a list of tuples. We'll do that here. Before we do anything, it's important to understand that our multi-index has two levels. Level 0 is the store level, and level 1 is the product level. We could have more, but in this example, we have 2. Now, let's say you just hate multi-indexes and you don't want to use them. You can use the resetIndex method with inPlace equals true to convert the index levels as columns and go back to using a plain old range index. Alright, so that covers our tutorial on multi-indexes. I hope you enjoyed this lecture. Now, if you want to revert back to our original data frame with a multi-index, you can use the setIndex method, passing in a list of column names to use as the multi-index. Now let's try selecting certain rows from our multi-indexed data frame. If you wanted to pick out the rows with keys sports dorks golf ball and superstore football, you can use .loc, passing in a list of tuples. If you wanted to pick out every row for sports dorks, you can use .loc, passing in the key sports dorks. But what if you wanted to pick out all rows where the product is football? In this case, you can't use .loc, at least not easily. But there is a method called XS, which lets you specify a key like football and tell Pandas which level of the index to search on. So for example, we can do storeproducts.xs, key equals football, level equals product. And if we wanted to retain both the store and product indexes in the result, we can set the drop level argument equal to false. Now let's take a look at a group by aggregate operation, since this is a more common way multi-indexes arise in practice. We'll start by building a data frame with 7 rows and 4 columns. Then we'll set stu equal to df.groupby by equals listab dot ag, and then we'll take the sum over c and the sum and mean over d. In this case, the row index is a multi-index, and so is the column index. If we wanted to select all columns representing a sum, we could use our handy XS method, but this time we have to specify axis equals 1, so Pandas knows to look for the key within the columns of Stu. Also, in this case, the column index levels don't have names, so we'll have to pass in a positional index into the level parameter. In other words, we need to tell Pandas to search for the key named sum in the second level of the multi-index, i.e. level 1. We could also do something like pick out columns for D by specifying key equals D and level equals 0. Now let's suppose you wanted to flatten the columns from a multi-index to a regular index. There's a lot of ways you can do this, but perhaps the easiest is to use the toFlatIndex method. For example, if we call stu.columns.toFlatIndex, we get back an index of tuples. We could take this a step further and use basic Python string joining and list comprehension to convert those tuples into strings separated by underscores. Setting stu.columns equal to our list of strings flattens the index how we want it. Alright, so we've looked at how to use multi-indexes, but we haven't really answered the question, why would you use a multi-index? This is a bit of a sore spot for me because I really care about performance, and you'd expect that a multi-index would provide significantly better performance than storing your data in 2 or more naive columns of a data frame. But from my testing, it really doesn't, at least as of the time I'm making this video. Now, there's still benefits to using a multi-index. The big one is probably self-documenting data. When you have a data frame with a multi-index, right away you know something important about the structure of that data. Also, multi-indexes play nicely with some other functions like stack and unstack, which we'll see in a future video. But for the most part, the benefits of using a multi-index are mostly superficial, at least for now, and I think that's a real missed opportunity for Pandas. In this video, we'll see how to use the functions pivot, pivot table, melt, stack, and unstack to restructure the shape of a data frame. Suppose you have a data frame df like this. There's a good chance you'll want to reshape that data to look like this. Here we converted the data from long format to wide format. Some people would say we converted the data from stacked format to unstacked format. For better or worse, there are a ton of ways to do this in Pandas. Perhaps the simplest method is to use the pivot method of a data frame. In this case, we call df.pivot, telling Pandas which columns we want to use for the row index, column index, and values. Now suppose df had slightly different data and looked like this. What do you think the same call to df.pivot would return in this case? Trick question, we actually get an error here, because there are multiple instances where multiple values in the input map to the same exact position in the output, and we haven't told Pandas how to deal with that. This is where the more general pivot table method comes in. Pivot table works just like pivot, but you can specify an aggregation function to tell Pandas how to deal with multiple values mapping to the same place. To make this more clear, suppose we call df.pivottable, setting index equals row, columns equals col, and values equals val, just like before, but here we also specify agfunc equals list. Here it's pretty obvious to see that 67 and 9 mapped to the same location because they had the same row and col values. Agfunc tells Pandas how to deal with those values, in this case wrapping them into a list. Also note that the combinations row 0 col 0 and row 1 col 1 didn't exist in df, so Pandas fills those entries with nan by default. Now, you're probably not interested in pivoting data just to build lists of values. More interestingly, you can use aggregation functions like mean, or sum, or size, or count, or a combination of all of them. This works just like doing normal data frame aggregation. So, for example, if you wanted to get the count and sum of elements mapping to cells in the output table, you could do something like this. As you could probably guess, Pandas supports this kind of pivot operation using multiple columns for the row index, column index, and values. So if you have input data like this, you can do crazy stuff like this. By the way, my column index in this data frame has 4 levels, which is pretty nuts. So far, we've been looking at ways to reshape a data frame from long to wide format. But what if we want to do the opposite? Go from wide to long format, i.e. unstacked to stacked format. For example, consider this data frame that shows 2 students' scores on 4 tests. If we wanted to reshape that data frame to look like this, the tool for the job is melt. Here's what that looks like. The most important parameter here is value vars, which should be a list of the columns you want to stack, in this case, John and Patty. In fact, that's literally all you need to provide for this function to work, although the output isn't very friendly without other information. Var name and value name tell Pandas how to name the new variable and value columns, and ID vars tells Pandas what other columns from the original data frame you want to keep in the result. Two other tools for reshaping data frames are the stack and unstack methods. For example, if you have a data frame of daily stock prices like this, and then you call df.stack, Pandas reshapes the data frame into a series, literally stacking the values of ABC, DEF, and GHI within each original row index, resulting in a 2-level multi-row index. Things get a little trickier when DF has a multi-index column. Consider this data frame. So stack's most important parameter is called level, and it tells Pandas which level or levels from the column index you want to stack into the row index. Let's see some examples, keeping in mind that our pets data frame has 2 levels in its column index: type with values dog and cat, and subtype with values Persian, calico, corgi, and lab. If we call pets.stack with level equals type, you can see how the first level, type, gets extracted from the column index and inserted into the row index, and the data realigns itself accordingly. Pretty much the same thing happens when you call stack with level equals subtype. Note that by default, stack is called with level equals -1, which automatically stacks the last column level into the row index. So in this case, pets.stack with no parameters returns the same thing as pets.stack level equals subtype. You can also call pets.stack with levels set to a list, like type, subtype, in which case both column levels are stacked into the row index, and the result is a series, not a data frame. Just as Pandas gives us a stack method for stacking column levels into row levels, it also gives us an unstack method for unstacking row levels into column levels. So where we have pets.stack level equals type, we can do almost the inverse operation with .unstack level equals type, although in this case, type becomes the second level of the column index, and all the nans created by stack get retained as columns with unstack. You have a data frame called schedules that represents the daily schedule of each student in a school. For example, if Ryan attends 4 classes, math, English, history, and chemistry, your schedules data frame will have 4 rows for Ryan in the order he attends each class. You have this idea that the sequence of class-to-class transitions affects students' grades. For instance, you suspect that Ryan would do better in his chemistry class if it immediately followed his math class instead of his history class. Determine the average and median chemistry grade for groups of students based on the class they have immediately prior to chemistry. Also, report how many students fall into each group. Here's the solution I came up with. Let's break it down. The first thing I do is insert a new column into schedules called prev class that tells the previous class for each student. The trick here is to group by student ID and then use transform with the series shift method so that for each student ID, the class series shifts forward one period. Then I group by class in prev class and aggregate taking the count of student IDs, average grade, and median grade. And lastly, I use the .xs method with key equals chemistry, axis equals 0, and level equals 1 to pick out class pairs that end with chemistry, and then I chain that with sort values med grade to make the output a little more insightful. You developed a multiplayer indie game called Thorn. Players compete in one of two venues, the ocean or the desert. You track the outcome of 5 games between 3 players in a data frame called games, and now you want to analyze the data. Convert the games data frame into a new data frame that identifies how many times each player placement occurs per venue, specifically with venue as the row index and player placed as the column multi-index. Here's the solution I came up with. Let's break it down. The first step is to call games.melt, setting ID vars equals venue, var name equals player, and value name equals placed. Conceptually, you could imagine this as stacking the columns Bella1, Billy Bob, and No Soup for You into a single column. Next, if we group the data by venue player placed, then aggregate the groups with size, we get back the count of rows in each group. This tells us how many times each player got each placement for each venue, amongst the triplets that actually occurred in the data. However, it'd be nice if we also had groups for triplets that didn't occur, like Desert Billy Bob 3rd, or Ocean No Soup for You 2nd. There's a few ways we can fix this, but one really cool way is, let's go back to step 1 and convert venue, player, and place to categoricals. Now when we group the data in step 2, all of those unobserved triplets are actually included in the result. At this point, step 2 is a data frame with a 3-level multi-index. If we reshape it using unstack with level equals the list player placed to move the player and placed levels out of the row index and into the column index, we get back our desired result. Given a series of product descriptions like birch table measures 3 feet by 6 feet by 2 feet, estimate the volume of each product. I came up with 2 solutions to this problem, both of which use regular expressions. Now, even though we didn't cover regular expressions in the course, I included this problem because once you do learn regular expressions, you'll want to know how to use them with pandas, and this will give you a good chance to see how they're useful. So here's the first solution. This bit here is a regular expression, and you can tell because the string has an R right before it. This bit, and this bit are called capture groups because they're enclosed with parentheses. Inside each capture group is a regular expression pattern, and in this case they're all /d plus. In regex, /d means any digit, so it matches any numbers 0 through 9, and plus means one or more matches. So when we do descriptions.str.extract and pass in this regular expression, it looks for one or more digits, followed by $x, followed by one or more digits, followed by $x, followed by one or more digits, followed by apostrophe. And what gets returned is a data frame with the values identified by each capture group. Looking at the first string in the descriptions, the regular expression matches this substring, and the capture groups pick up these substrings. Now, str.extract returns strings, so we'll convert those to ints. And then we can do dims.product axis equals 1 to do row products, calculating the volume of each product. So my second solution is nearly the same, except it uses str.extract all with one capture group. Obviously, this returns every matching occurrence of one or more digits followed by an apostrophe, which is a little less bulletproof than the previous solution, but it works for this example. Then I convert dims from strings to ints, just like before. And since the index of dims is a multi-index of input row match number pairs, I want to group the data by input row, so level 0 of the multi-index, and aggregate the groups taking the product of series values. You run an e-commerce site called shoesfordogs.com. You want to do some analysis of your visitors, so you compile a data frame called hits that represents each time a visitor hits some page on your site. You suspect that the undocumented third-party tracking system on your website is buggy and sometimes splits one session into 2 or more session IDs. You want to correct this behavior by creating a field called session group ID that stitches broken session IDs together. 2 sessions A and B should belong to the same session group if 1. They have the same visitor ID, and 2. Their hits overlap in time, or the latest hit from A is within 5 minutes of the earliest hit from B, or vice versa. Also, associativity applies. So if A is grouped with B and B is grouped with C, then A should be grouped with C as well. Create a column in hits called session group ID that identifies when hits belong to the same session group. Here's the solution I came up with. Let's break it down. The first part of my solution is to sort the hits data by visitor ID and date time in that order. This isn't a necessary step, but it makes the data a little easier to digest, and you can actually see where some session breaks occur. For example, for visitor 1, session 102 ended just 4 minutes before 101 began, so we're going to want to stitch those into the same session group. Another example is, for visitor 3, you can see where the session IDs flip between 302, 303, and 300. Ultimately, these should all get stitched into the same session group, because 302 had the earliest and latest hit for this visitor. So the first real part of the solution is to group the data by visitor ID and session ID, and then aggregate the groups taking the min and max of each datetime. I put this in a variable called sessions, and it gives us a look at one row per session as defined by our broken tracking software. Next, I sort the sessions by visitor ID and datetime min in that order. My next step is to add 5 minutes to datetime max, which we can do with sessions.datetime_max plus pd.timeDelta minutes equals 5. This basically tells us, if you look at some session, that if any subsequent session for the same visitor starts on or before this datetime, that they should be grouped together. For example, let's look at session 403. The first one started by visitor 4. The session ended at 12:21 a.m., so any subsequent session for visitor 4 that started on or before 12:26 a.m. should get grouped with session 403. In this case, that means both sessions 400 and 402 should get grouped with 403. In order to create a link between these, we can take a cumulative max of datetime max P5. That ends up looking like this. Now, we still haven't quite linked session 400 and 402. To do that, we need to get the previous datetime max P5 cum max within each visitor ID, which we can do like this. Then we check if each session should be grouped with the one in the previous row by checking if its datetime min is less than or equal to datetime max P5 cum max prev. Now, wherever you see a true value, we want to give that record the same ID as the one before it. And wherever you see a false value, we want to create a new ID. A trick to do this is to negate these boolean values and then take their cumulative sum. Remember, false is synonymous with 0 and true is synonymous with 1, so it's like taking a cumulative sum of zeros and ones. The last step is just to insert the session group IDs back into the hits table, which we can do with a simple inner join. You own a gym for pregnant women called obgym, and you recently opened a second location. You'd like to analyze its performance, but your reporting software has given you the sales data in an awkward format. Reshape it into a data frame like this. I came up with two solutions to this problem. Here's my first. In this case, we want to reshape the data from long to wide format. So the first thing we do is pivot the sales data with index equals date and columns equals store ID. Obviously, this creates some columns we don't need, so we can chain that with drop in a axis equals 1, which drops columns with nan values. Right now, we have a multi-index for the columns. We can flatten that index just by setting the columns equal to a list of strings like this. But if we want to make that a little more dynamic, we can use list comprehension combined with an if-else statement and some f strings like this. In English, this says, for x and y in sol1.columns, keep in mind sol1.columns is basically a list of pairs. If the last character in x is either a 1 or a 2, then make a new string by concatenating x minus its last character and y with an underscore. Otherwise, concatenate all of x and y with an underscore. Here's my second solution. Here I set the index of sales as date, store ID pairs. Then I can call unstack, which by default pulls the last level of the row multi-index, in this case store ID, out of the row index and into the column index. From there, we clean it up just as we did in the last solution. You track the whereabouts of 100 individuals in a data frame called whereabouts. Each person has a corresponding list of place IDs indicating the places they visited in the recent week. You also track which places have been exposed to COVID-19 in a list called exposed. For each person, identify the places they visited which have been exposed. Make this a new list column in whereabouts called exposures. I came up with two solutions to this problem. Here's my first. Let's break it down. So, one line, pretty good, right? Basically, all this does is it uses apply to apply a function to each value in the places column. The function we apply is one we make up on the fly with lambda. In this case, the input x is a list. If we convert that to a set, and then convert the list of exposed places to a set, we can get the intersection of those two sets, i.e. the values in both sets, and then wrap that with list to convert back to a list. Here's my second solution. It's a little bit longer. Now, the strategy here is to expand whereabouts so that we get one row per person place pair, then filter the rows where place is one of the exposed places, and then clean up the data from there. So the first step is to expand whereabouts, which we can do using the explode method with column equals places. Next, we set filtered equal to expanded.loc square brackets expanded.places.isIn exposed to select rows where place is one of the exposed places. Then we group the data by person ID, aggregating the exposed places with a list. We'll also rename the places column to exposures. Then we merge back to whereabouts using a left join as a way to insert this column of exposures into the whereabouts data frame. Unfortunately, you can't use fill_in_a to fill nans with an empty list, so to replace these nans with empty lists, we have to do something like this. Here, lambda x returns x if it's already a list, otherwise it returns an empty list. Given a series called pickle, replace nans using the following algorithm. For each nan, get the nearest non-nan value before and after it, and then replace nan with the minimum of those two non-nan values. For nans on or near the endpoints of the series, use the closest non-nan value. Here's the solution I came up with. Let's break it down. Series has a method called ffill, which stands for forward fill, that shifts the series values forward to fill nans. Similarly, there's a method called bfill that stands for backfill, that does the same thing but backwards. So the first step in my solution is to assign the result of ffill to a variable called prevs, and assign the result of bfill to a variable called next. Then, we need to get the minimum of each pair of values from prevs and nexts. If we put the series in a list, we can concatenate them into a 2-column data frame using pd.concat with axis equals 1. Then we can chain that with .min axis equals 1 to get the row-wise mins. Note that nan in the last row is ignored and the min returned is 1.9. Lastly, we can pass the series into pickle.fill_in_a in order to fill missing values with matching index labels. You own a national restaurant chain called Apple Wasps. To increase sales, you decide to launch a multi-regional television marketing campaign. At the end of the campaign, you have a table of commercials indicating when and where each commercial aired, and a table of sales indicating when and where customers generated sales. In order to analyze the performance of each commercial, map each sale to the commercial that aired prior to the sale in the same region. Here's the solution I came up with. Let's break it down. So what we want to do in this case is something called a rolling join. In Pandas, it's implemented with the function merge as of. I'll explain what that is in a second, but first we need to sort commercials and sales by date time. Now visualize the sales data like this, and the commercials data like this. What we want to do is, for each region, roll the sales data backwards to the nearest commercial. This is exactly the functionality provided by merge as of. So in this case, we call pd.mergeAsOf, left equals sales, right equals commercials, on equals date time, by equals region, and direction equals backward. And we get back a table with every sale and the nearest commercial ID on or before the sale date in the same region. Define a person's family IQ score as 0.5 times IQ score plus 0.5 times relatives IQ score, where relatives IQ score is the average IQ score of that person's parents, full siblings, and children. Given a data set of people and their IQ scores, determine who has the highest family IQ score. Here's the solution I came up with. It's kind of long, but I think the code's longer than the actual logic, so let's go ahead and break it down. Here's the strategy. I want to build a data set of moms with ID, mom IQ, a dataset of dads like ID, dad ID, dad IQ, a dataset of siblings like ID, sibling IQ, and a dataset of children like ID, child IQ. And then I want to concatenate those into one tall data frame of relatives that has every ID, relative IQ. From there, I can calculate the average relative IQs, pipe those back into the person's data frame, and calculate each person's family IQ score. So as a first step, let's build that moms table which has ID, mom IQ, and only rows where mom ID and mom IQ exist. For that, I can do pd.merge, setting left equals person's ID mom ID, right equals person's ID IQ, how equals inner, left on equals mom ID, right on equals ID, and suffixes equals the list, empty quotes, underscore relative. Note that I'm inner joining the person's data frame to itself, but in the left table I join on mom ID, and in the right table I join on ID. Also, the output isn't exactly what we said we wanted, but it has more or less the same meaning. Then we do nearly the same thing to build a table of dads. To get full siblings, we have to join them both mom ID and dad ID. We also have to drop rows where mom ID or dad ID is NA. And we have to exclude matches where ID from the left table matches ID from the right table, because you can't be a sibling of yourself. And then for children, we concatenate the children of fathers and the children of mothers into a single data frame. Notice the column renaming that happens, where dad ID becomes ID, and ID becomes ID underscore relative. Now we can combine all the relatives into a single data frame. And then group the data by ID, measuring the average IQ of each person's relatives. Now we need to get the average relative IQs into the person's data frame, which we can do with some simple index alignment. We'll start by setting the index of persons to be ID, then we just set average rel IQ equal to average relative IQs. And then we can calculate each person's family IQ score. Lastly, we identify the person with the highest family IQ score using index max, and the winner is person 83. Given a data set of concerts, count the number of concerts per artist venue pair per year month. Make the resulting table be a wide table, one row per year month, with a column for each unique artist venue pair. Use the cross product of the artists and venues series to determine which artist venue pairs to include in the result. I came up with two solutions to this problem, so here's my first solution. So the first thing I do is determine the set of artist venue pairs to consider. These will be the cross product of values in the artist series with the values in the venue series. One way to get a cross product of two series is to use the from product constructor of multi-index like this. Now, if I do a left join from concerts onto this multi-index, I'll get back only concerts with the artist venue pairs I care about, including pairs that don't have any concerts. In order to do that, I need to convert the artist venues multi-index into an empty data frame and set it as the left table. I'll set the row index of concerts as artist venue and make that the right table. I'll join on artist and venue, and I'll specify the join type as left. Now I'll infer year month from date using concerts2.date.dt.toPeriod, open parens, open quotes, capital M for monthly. And then lastly, I'll pivot concerts2 using index equals year month, values equals date, columns equals the list artist venue, agfunc equals count, fill value equals 0, and drop in A equals false. Here's my second solution. The first thing I do is convert the artist and venue fields in concerts to categoricals, whose categories are given by the artists and venues series. Notice that this converted the venue Red Rocks to Nan, because you can't have a categorical with a value that's not in its list of categories. So the second thing I do is drop rows with a Nan value. Then I insert a year month field just like before. And lastly, I use pivot table just like before. In this case, every combination of artist category, venue category is included in the column set, even categories that didn't have observations in concerts2, like the rolling sums.